beyond the last blue memory of Earth, beyond the orbit of Neptune, beyond the faint dust where Pluto moves through its long, cold year. A small machine is still drifting outward. It carries no warmth of its own, no window, no voice, only instruments, old metal, and a direction that will never turn back. The sun behind it has become less like a star and more like a pale idea, a point of light among other points, still pulling gently, still fading into the dark. Before this quiet journey moves any farther, take a moment to settle in. If this kind of slow voyage through deep space helps the night feel a little wider and a little softer, consider subscribing, leaving a like, or sharing it with someone who listens to the universe in the dark. And wherever this reaches you, whether it is very late, just after midnight, or in the still hour before morning, it is pleasant to imagine all those separate rooms under separate skies, connected for a while by the same distant stars. Turn the lights down if they are still bright. Let the room become simple. A fan may be moving somewhere nearby. A blanket may already be warm. The body does not need to follow every name or every number. It only has to drift with the motion of the story, slowly outward, from the familiar gravity of home toward the deeper places where sunlight becomes thin. There is no sharp edge where the solar system ends. There is only a long fading, a shore made not of sand, but of charged particles, old spacecraft, and silence. Out there, the first part of the journey is already underway, carried by the last machines still leaving home. A machine leaving home does not look heroic from the outside. It does not burn like a star or cut a shining road through the dark. It is small, cold, and almost silent, moving because of speed given to it long ago, carrying the memory of launch towers, radio commands, and a planet that now lies far behind the Sunday. New Horizons is one of those machines. It began as a visitor to Pluto, aimed at a world so distant that for much of human history it was not even imagined. The spacecraft crossed the inner solar system with the help of Jupiter, borrowing speed from the giant planet's gravity before continuing toward the faint edge where sunlight grows weak. When it passed Pluto, the old point of light became a place with mountains, plains, haze, and frozen nitrogen moving slowly across the surface. Charon, its largest moon, appeared not as a footnote, but as a world with cliffs and dark polar ground. For a brief time, a part of the outer dark had texture. Then the encounter ended. That is the nature of a flyby. A spacecraft crosses a world's neighborhood once, gathers what it can, and then keeps going. There is no orbit to settle into, no second pass waiting a few weeks later. Pluto fell behind. The cameras looked elsewhere. New Horizons moved onward through the Kuiper Belt, the wide outer region where icy bodies preserve old material from the solar system's beginning. Later, it passed Arakoth, a small, reddish object shaped by gentle contact in the cold. The meeting was quiet, almost delicate. Two lobes joined together, not shattered, not melted, but left in a shape that spoke of slow beginnings. Beyond that, the spacecraft keeps moving outward. Its instruments do not make it large. Its antenna does not make it less alone. It is simply a small human object passing through a place where the sun is no longer a warmth, only a direction. Long before New Horizons, there were the pioneers. Pioneer 10 and Pioneer 11 crossed the outer solar system when space exploration still carried the feeling of first footsteps. Pioneer 10 went to Jupiter and returned images and measurements from a planet that had always been visible from Earth, yet never truly close. It found a world with a magnetic field vast enough to shape space around it, a giant giving off more heat than it received from the Sunday. That detail matters. Jupiter is not just a cold ball reflecting light. Deep inside, it still carries leftover heat from formation, a buried warmth slowly escaping through clouds that never become solid ground. Pioneer 11 followed a different road. It passed Jupiter and went on to Saturn, where rings, moons, and magnetic fields turned from distant shapes into measured places. Its cameras saw a system of pale arcs and shadows, a planet whose rings were not ornaments, but countless particles moving in careful paths. Afterward, it too went outward. The pioneers became unreachable in time. Their signals stopped. Their missions ended from Earth's point of view, but not from the point of view of motion. A silent spacecraft does not stop being there when the last radio wave fades. It continues, obeying gravity, inertia, and the deep patience of empty space. Somewhere beyond the familiar planets, the pioneers are still moving. They no longer send back temperatures, particle counts, or faint confirmations that their old systems are awake. They have become drifting objects, dark against dark, carrying plaques that were once meant as messages. Those plaques show a human form, the position of the sun, and a hope that some other intelligence might one day understand symbols engraved by a young species on a small world. The hope is almost too large for the object carrying it. Voyager 1 and Voyager 2 carried a different message. Their golden records were made for distances that no human life can follow. They hold sounds, images, greetings, music, and the attempt to place Earth inside a container small enough to bolt to the side of a spacecraft. It is a strange thing to imagine. Ocean waves, heartbeats, footsteps, wind, and voices crossing the outer darkness on a machine that has no ears. Voyager 1 went first in one sense, though Voyager 2 left Earth a little earlier. Their paths were shaped by a rare alignment of the outer planets, a geometry that allowed one world's gravity to bend the journey toward the next. Jupiter came first, with its banded atmosphere, its storm larger than Earth, and its moons moving like a small system of their own. Io showed active volcanoes, not ancient scars alone, but present eruptions, sulfur and heat rising from a moon pulled and flexed by Jupiter's gravity. Europa hinted at a hidden ocean beneath ice. Ganymede and Callisto carried old surfaces marked by impacts and time. Saturn followed, pale and wide, surrounded by rings that seemed smooth from far away and granular in truth. The Voyagers passed through a system full of small moons, ring gaps, shepherding gravity, and Titan's orange haze. For Voyager 1, Saturn was the turn that lifted it away from the plane where most planets move. After that, its path no longer led to Uranus or Neptune. It headed out, above the familiar flatness of the solar system, toward the boundary where the sun's influence would become thin. Voyager 2 continued. It remains the only spacecraft to have visited Uranus and Neptune closely. Uranus appeared with a muted blue-green disk and a tilted system. Its rotation turned almost on its side. Neptune was darker, windier, more active than many expected, with clouds and storms moving across a planet so far from the sun that daylight there is only a faint version of day. Triton, Neptune's large moon, showed a frozen surface and signs of geyser-like activity, another cold place that was not simple after all. These encounters changed the outer solar system from a diagram into a set of worlds. Before them, the distant planets were mostly disks in telescopes, colors, dots, and calculated orbits. After them, they had weather, rings, moons, storms, haze, cliffs, cracks, and surfaces that could be studied. The solar system became less like a clean map and more like a long corridor of different rooms, each one stranger than the last. But the most patient part of the Voyager story began after the planets. Once the bright targets were behind them, the spacecraft entered a slower kind of exploration. They were no longer arriving at worlds. They were measuring the space between worlds, then the space beyond them. Particles, magnetic fields, plasma waves, the fading breath of the Sunday. The sun does not end at the last planet. Its wind moves outward, a flow of charged particles streaming from the star in every direction. Near Earth, that wind is part of space weather. Farther out, it becomes a pressure pushing against the thinner material between the stars. For a long time, Voyager 1 moved through this outer bubble, crossing regions where the solar wind slowed, changed, and became disturbed. Then, in the early 21st century, it passed into interstellar space, the first human-made object known to do so. That phrase can sound too clean. Interstellar space is not a wall crossed in a single bright moment. It is a change in environment. The particles around the spacecraft begin to come less from the Sun and more from the galaxy. The magnetic field behaves differently. The plasma has another density, another character. The machine is still close to the Sun by the standards of stars, but it is no longer inside the same kind of wind. Voyager 2 crossed later, carrying its own measurements through a different part of the boundary. Together, the two spacecraft gave the heliosphere depth. They showed that the Sun's outer shelter is not a perfect sphere, not a glass bubble, not a simple border drawn around the planets. It is shaped by movement, pressure, magnetism, and the flow of the interstellar medium pressing against it as the solar system travels through the galaxy. There is something calm in that image. The Sun, all fire and light from Earth's sky, becomes a star moving through a thin galactic sea, wrapped in its own wind. The planets follow inside that moving shelter. Dust crosses it, cosmic rays strike it. Old spacecraft pass through its outer layers and send back faint measurements that take many hours to arrive. Every signal from Voyager is old by the time it reaches Earth. It leaves the spacecraft as a whisper of radio energy and spreads across billions of kilometers. By the time it is received, it is weak beyond ordinary imagination, gathered by great dishes listening for a voice almost lost in background noise. Nothing about this is fast anymore. A command sent from Earth travels outward through empty space, and the reply returns only after the turning of a planet that the spacecraft can no longer see as home. The power aboard the Voyagers is fading. One instrument after another has gone quiet, or will go quiet. Heat becomes precious. Electricity becomes something to ration. Engineers on Earth do not command a young machine now, but an old one, keeping it alive by choosing which parts may sleep so others can continue speaking a little longer. This is not failure. It is aging at interstellar distance. The spacecraft were never meant to last forever. No object does. What makes them different is that their silence will still have direction. Even when the last instrument shuts down and the last signal never comes, they will keep moving through the dark. Voyager 1 will drift toward the region of the distant Oort cloud, if that cloud is truly there, as models suggest. It will take thousands of years to pass through the outer comet reservoir surrounding the Sunday. Later, much later, it will move in the general direction of another star, not to arrive in any human sense, but to pass through its neighborhood after a span of time longer than civilization has existed. Voyager 2 has its own future, another long path through the galaxy. Pioneer 10, Pioneer 11, New Horizons, Voyager 1, Voyager 2. Each is a small object with a different course, yet all belong to the same quiet category. They are pieces of Earth that no longer return. Behind them, the sun continues to shine. Around it, planets circle, moons turn, comets wait in cold storage, and Earth rotates through its ordinary nights. Ahead of them is not a destination. Not really. It is distance itself. The first lesson of deep space is not that the universe is hostile or empty or impossible to cross. It is that leaving home happens slowly. Light fades by degrees. Warmth becomes memory. And far beyond the planets, the machines keep going. The farther a spacecraft travels from the planets, the less the solar system resembles the neat drawing often seen in books. It is not a flat arrangement of circles, and it is not a set of worlds floating in a clean black room. Around the sun, there is motion, there is pressure, there is a wind that never stops. That wind begins at the star itself. From the sun's outer atmosphere, charged particles stream outward in all directions, moving past Mercury, past Earth, past Jupiter, and then farther still, out beyond the place where the giant planets become faint points. Near Earth, this flow is part of space weather. It bends around magnetic fields, shakes the upper atmosphere, and sometimes helps paint aurora across polar skies. Far from Earth, it becomes something quieter and larger. It becomes the shape of the sun's reach. The heliosphere is the name given to that reach. It is not made of glass. It does not have a surface a spacecraft can strike. It is a vast moving region filled with solar particles and magnetic fields. Harried outward by the star and pressed from outside by the thin material between the stars. The whole structure travels with the solar system as the sun moves around the center of the Milky Way. The planets do not simply circle a star. They move inside a star-made shelter, crossing the galaxy within a bubble of wind. That bubble is not still. The sun rotates. Its magnetic field twists. Eruptions rise from its surface and send disturbances outward. The solar wind changes with the star's 11-year cycle, sometimes stronger, sometimes weaker, sometimes carrying storms that began near the sun and arrived years later at distances where no sunlight feels warm. At the outer boundary, these changes do not vanish. They arrive stretched thin by distance, but they arrive. Before the heliopause, there is the termination shock. This is where the solar wind slows suddenly, not because it has run out, but because it has begun to feel the pressure of the material outside. A shock in space does not need air. It is a change carried through plasma, a river of charged particles shifting speed and density as it meets resistance. The flow from the sun becomes slower, more disturbed, and the region beyond it is called the heliosheath. The word sounds technical, but the image is simple enough. The sun's wind has reached rough water. The heliosheath is wide, uneven, and difficult to picture because no telescope can stand outside it and take a clear photograph. It must be studied by particles, fields, and faint signals from spacecraft moving through it one point at a time. Voyager 1 passed through one part. Voyager 2 passed through another. Their paths were separated. Their instruments were not identical, and the boundary they crossed was not a smooth shell. Together, their measurements made the edge of the solar system feel less like a line and more like weather. There are particles from the sun moving outward. There are particles from the galaxy trying to come in. There are magnetic field lines draped and bent along the edge. Galactic cosmic rays, high-energy particles from beyond the solar system, push inward and become more common as the sun's shielding weakens. The heliosphere does not block them all. It softens the storm. It filters. It changes with time. For Earth, this shelter is far away and yet intimate. Life under the atmosphere does not feel the heliosphere directly, but it exists inside its protection. The Earth has its own magnetic field, its own air, its own layers of defense. Still, beyond all of those, the sun has made a larger room in the galaxy. Every planet, every comet, every grain of dust bound to the sun spends its existence inside that moving room, unless it wanders far enough to leave. This is why the Voyagers matter after their planetary encounters. Their cameras no longer return close views of moons and storms. Their value becomes quieter. They are no longer showing a place. They are feeling a boundary. Voyager 1 crossed the heliopause first. The spacecraft did not send back a photograph of a wall. Instead, instruments recorded changes in the surrounding environment. Solar particles dropped. galactic particles rose. Plasma measurements and magnetic readings pointed toward a different region of space. The spacecraft had entered the interstellar medium, the extremely thin matter that fills the space between stars. Thin is almost too heavy a word for it. A cubic centimeter of interstellar space may contain far less matter than any laboratory vacuum on Earth. Yet it is not nothing. It has atoms, ions, dust, magnetic fields, and waves. It remembers supernovae. It carries material once thrown out by old stars, and material that may someday become new stars. It is the background through which the solar system moves. Voyager 2 crossed later, and its passage mattered because one of its plasma instruments could still measure the solar wind in a way Voyager 1 could not at the same boundary. From that second crossing came another view of the same invisible shore. Not identical, not symmetrical. The heliopause seemed to breathe and ripple under changing pressure from inside and outside. The old idea of a smooth, comet-shaped bubble had to give way to something messier, more alive with motion. The sun is not unusual in having a wind. Other stars have winds too. Red dwarfs, small and dim, may flare with bursts that reshape the conditions around their worlds. A star is never only a lamp, it is also a source of particles, pressure, magnetism, and change. Every planetary system may have its own weather at the edge. Around another star, a different astrosphere may press against a different interstellar flow. A planet's habitability is not only a matter of distance from its star, it also depends on what that star throws into space and what the planet can hold. The solar system is moving through a local region of interstellar gas, a cloud so thin that the word cloud feels almost misleading. The gas is warm by ordinary standards, but so sparse that it would not warm a hand. The sun's magnetic bubble keeps much of it away from the planets, but the encounter still shapes the outer boundary. The heliosphere is not a monument built once, it is a negotiation happening constantly, written in particles too small to see. A boundary like this changes the meaning of home. Home is not only rock, ocean, atmosphere, or orbit. It is also a protection extending far past the planets. Close to Earth, the sun is day. Farther out, it is a disk. Beyond Neptune, it is only the brightest star in a dark sky. At the heliopause, even the sun's wind has grown tired enough to yield. Yet yielding is not disappearing. The star remains behind every measurement. It is present in the particles that fade, in the magnetic field that bends, in the cosmic rays that grow stronger when its shelter thins. The last shore of the solar system is made from this balance. Not solid against empty, not light against dark, but one flow meeting another in silence. The Voyagers continue beyond it. They are not free of the sun's gravity, not yet in the deepest sense, and they will remain connected to it for a long time by motion and memory. But the space around them has changed. The wind that once came from home is no longer the main voice. The galaxy has become the surrounding medium. From here, the next step outward is toward other suns. Nearby stars wait in the same thin sea, each carrying its own light, its own wind, its own small region of order against the dark. The nearest of them is close by the standards of the galaxy, and impossibly far by the standards of machines. Still, the path leads there, away from the fading shore and into the dim red light of the neighboring stars. The nearest other suns are not bright in the way imagination might expect. From Earth, Alpha Centauri is one of the familiar southern lights, a point that appears steady to the eye. It does not look like a doorway. It does not announce that beyond it lies the first true neighboring system. The first place where sunlight is not the sun's light at all. Seen from much closer, the point separates into motion. Alpha Centauri A and Alpha Centauri B circle a shared center of mass. Two stars bound together, in a slow gravitational dance. One is close to the Sun in size and color, a yellow-white star with a little more brightness. The other is cooler, smaller, and more orange, giving less light but still burning with the steadiness of a main sequence star. From a world in that system, if such a world had the right orbit, the sky would not belong to one sun alone. There would be a primary day, and somewhere else in the heavens, another star bright enough to change the darkness. Their separation shifts as their orbit carries them inward and outward over decades. At their nearest, there is still room between them for stable paths, if those paths are carefully placed. At their farthest, the gap stretches wider, turning the pair into a spacious binary rather than a crowded one. Yet gravity from two suns complicates everything. Dust, rock, and newborn planets must find order in a place where the pull of the sky changes over long cycles. No confirmed planet has yet settled the matter around either Alpha Centauri A or B. There have been hints, possible signals, quiet disturbances in data, and then caution. This is how the nearest system remains strangely hidden. It is close enough to be named with ease, close enough for its light to cross the distance in a little more than 4 years, and still too far for a clean inventory of its smaller worlds. The third star is different. Proxima Centauri is the closest known star to the Sun, but it is too faint to see with the unaided eye. It is a red dwarf, small and dim, carrying only a fraction of the Sun's mass and light. If the larger Alpha Centauri stars are lamps in the neighboring darkness, Proxima is an ember set far to the side. It moves with them across the galaxy, but at a wide distance, like a quiet outer member of the same family. Around this faint star, at least one planet is known. Proxima Centauri b is not large. It is close in mass to Earth, moving around its red star in a short year of only 11 days. The orbit sounds dangerously tight until the star itself is remembered. Proxima is so dim that a planet must stay near it to receive even a modest amount of warmth. The habitable zone of a red dwarf lies close to the flame. That phrase, habitable zone, can be misleading if it is heard too warmly. It does not mean forest, ocean, cloud, or life. It means only that, under the right conditions, a rocky world might receive enough starlight for liquid water to exist somewhere on or near its surface. It is a narrow physical allowance, not a promise. Around Proxima, the allowance comes with difficulties. A planet so close to a small star may be tidally locked, keeping one hemisphere turned toward the light and the other turned forever away. The day side would receive the long red stare of the star without sunset. The night side would face deep cold. Between them, perhaps, a band of softer conditions could exist if an atmosphere were thick enough to move heat around the globe. Winds would not simply be weather. They would be the planet's attempt to survive the difference between permanent day and permanent night. But Proxima is not a quiet ember. Red dwarfs can live for immense spans of time, far longer than stars like the Sun, yet their youth and even their maturity may be marked by flares. Proxima can release sudden bursts of radiation that wash over close planets. Ultraviolet and X-ray light can erode atmospheres, change chemistry, and strip away the gentler conditions that liquid water would need. A magnetic field might help, if the planet has one. A dense atmosphere might help if it has not already been thinned. The truth is that observations do not yet give a full answer, so Proxima b remains suspended between possibility and severity. It is near enough to become a symbol, but not near enough to become familiar. Models can describe climates. Telescopes can measure the star. Radial velocity data can reveal the planet's tug. But no one has seen its surface. No ocean has been confirmed there. No cloud has been watched crossing its face. It is a measured world, not a known one. There are other possible companions in the Proxima system. A very small inner planet candidate, often called Proxima d, has been reported from tiny shifts in the star's motion. Its signal is delicate, the kind that must be separated from the activity of a restless red dwarf. A farther candidate has also been discussed: a colder world or sub-Neptune on a long orbit, though its status remains uncertain. Around a star like Proxima, even discovery feels like listening for a soft footstep beside a storm. This is part of the difficulty of red dwarf systems. The stars are common. Most stars in the Milky Way are red dwarfs, low mass, and faint, burning slowly through time. If they hold planets, and many do, then a large fraction of the galaxy's rocky worlds may live under red light. Their years may be short, their skies may be flare-scarred, their habitable zones may sit so close to the star that tides, magnetism, atmosphere, and radiation all become part of the same problem. The nearest other sun, therefore, teaches a quieter lesson. The search for another Earth does not lead first to a twin of Earth. It leads to a small red star with a restless surface, and to a planet that may have one face in dim red daylight and one face in night. It leads to questions that cannot be softened too much. Water may be possible. Atmosphere may be possible. Survival may be possible. But possible is not the same as gentle. Still, the distance draws attention. 4 light-years is almost nothing in the scale of the galaxy, and still too far for ordinary spacecraft. A radio signal would need years to cross it. A probe moving at the speeds of the old outer planet missions would need tens of thousands of years. This is why concepts such as light sails return again and again to Proxima. A tiny craft pushed by a powerful laser might cross the gap in decades rather than millennia, pass through the system without stopping, and send its findings home as a whisper of light. For now, Alpha Centauri remains a nearby mystery rather than a destination. Its larger stars shine together, still withholding any confirmed small worlds. Proxima glows at the edge of the system, faint and active, holding at least one planet in the close red zone where warmth and danger arrive from the same star. The whole system sits close enough to feel almost local, and far enough to remind every measurement of its limits. Behind the outward-moving spacecraft, the sun fades. Ahead, the neighboring stars do not become easier when they become nearer. They become more detailed, more conditional, more strange. The first step beyond the solar system is not into a simple second home. It is into another kind of starlight, where even the closest world remains half hidden, turning in the red glow of a star, too faint for human eyes. The stars just beyond the nearest neighbor do not gather into a bright crowd. They come one by one, most of them small, cool, and faint, hidden from the naked eye, even though they sit close by galactic standards. The sun is not moving through a region filled with blazing twins. It is moving through a neighborhood of embers. Barnard's star is one of them. It lies only about 6 light-years from Earth, close enough to belong to the immediate surroundings of the sun, yet it is too dim to be seen without a telescope. It is a red dwarf, old, small, and quiet, compared with younger stars of its kind. Its light is weak, its surface is cool. If placed where the sun is, it would not give Earth anything like Earth's familiar day. The world would sit under a dull red glow, more like the last color of a dying coal than the white warmth of noon. What makes Barnard's star stand out is not brightness, but motion. Across the sky of Earth, it has one of the fastest apparent motions of any known star. Year by year, its position shifts against the deeper background. This is partly because it is near, and partly because it is truly moving quickly through space. It is approaching the solar system now, and in the distant future, it will come closer than it is today, passing through the local stellar neighborhood like a faint red traveler. For a long time, Barnard's star carried a different kind of attraction. It seemed like exactly the sort of place where a nearby planet might be found. Decades of claims rose and fell around it. Some were errors in measurement. Some were hopeful signals that did not survive better data. This is often how astronomy moves at the edge of detection. A star wobbles by a tiny amount. An instrument listens. A pattern appears. Then the pattern must endure years of checking, noise, stellar activity, and the slow discipline of doubt. The old idea of a cold super-Earth around Barnard's star has now given way to a different confirmed world. Barnard B is much smaller than Earth and orbits very close to its faint parent star. Its year lasts only a few Earth days. It is not a comfortable world. Even around a red dwarf, such closeness means heat, and the planet lies well inside the region where liquid water would be expected to remain stable on a surface. If it has a surface that could be walked in imagination, it would not be a quiet snowfield under red light. It would be a tight, inner world, baked by proximity, turning around an old star with almost clock-like speed. That change in the story matters. It shows how the nearest stars do not offer simple answers just because they are near. A nearby system can be watched for generations and still keep its architecture hidden. Around Barnard's star, there are hints of additional small worlds, but hints are not planets until the evidence holds. The star remains a lesson in patience. A little farther out lies Wolf 1061, another red dwarf, dim and ordinary in the larger census of the galaxy. Ordinary does not mean unimportant. Red dwarfs are the most common stars in the Milky Way. And if their planets can be understood, then a large part of planetary nature can be understood. Wolf 1061 is not visible from Earth without optical aid, yet it holds a small system of known planets, each revealed not by direct sight, but by the slight pull they exert on their star. The inner planet circles close to the red light, completing its orbit in only a few days. At such a distance, starlight and stellar particles arrive with little room for gentleness. A rocky surface may be stripped, heated, and exposed. If an atmosphere once formed there, it may have been altered or lost. Red dwarf planets close to their stars live inside a narrow conflict. They need closeness for warmth, but closeness brings tides, flares, and the slow erosion of the air around them. Farther out is Wolf 1061c, the more discussed world. It is a super-Earth, several times more massive than our planet, moving around its star in less than 3 weeks. It receives less light than Earth receives from the Sun, but because its star is small and cool, the planet sits near the region where liquid water might be possible under the right atmospheric conditions. That phrase has to remain careful. A planet can be in the habitable zone and still be frozen, scorched, airless, poisonous, or locked in a climate that never becomes mild. On Wolf 1061c, gravity would likely be stronger than on Earth if the planet is rocky. Landscapes, if they exist, might be lower and heavier, with mountains pressed into broader shapes over geological time. An atmosphere, if present, could move heat from the star-facing hemisphere into the dark, especially if the planet is tidally influenced. Clouds might gather along a boundary between day and night. Ice might creep outward from the colder side. Oceans, if any exist, would depend on the balance between pressure, greenhouse gases, rotation, and the red dwarf's changing moods. There is no need to make the planet more welcoming than it is. No ocean has been confirmed there. No air has been measured. No color is known. The world is a mass, an orbit, and a possibility shaped by models. But possibilities can be scientifically useful without becoming fantasies. They show which questions matter. How much atmosphere can a super-Earth hold near a red dwarf? How does tidal locking change climate? How often do small stars flare strongly enough to damage nearby planets? The outer known planet in the Wolf 1061 system moves on a longer, more stretched path. It is heavier, colder, and less clearly Earth-like, perhaps closer to a small Neptune, depending on its true radius and composition. Its orbit carries it through changing distances from the star, so any climate there would be pulled between long cold intervals and closer passages. It is not the gentle world a hopeful search might prefer. Between Barnard's star and Wolf 1061, the nearby galaxy becomes less familiar and more honest. The closest stars are not lined with second Earths waiting in plain view. Many are dim, their planets are tight, heavy, hot, cold, or only partly known. Their signals are small enough to be confused with stellar activity. Their atmospheres, if they have them, may be the hardest part to keep and the most important part to know. Still, these systems are valuable because they are near enough for the next generation of telescopes to revisit. Radial velocity instruments can watch for the slow pull of planets. Transit surveys can search for a planet crossing in front of its star, though many worlds never line up that way from Earth. Infrared telescopes may someday separate the faint warmth of a planet from the glare of its star. Spectra may one day carry hints of air, clouds, water vapor, carbon dioxide, or the absence of all of them. From the edge of the solar system, these nearby red stars would not look like destinations. They would be points in the dark, some barely brighter than the background. Yet around them, planets move through short years, close tides, and dim light. Some are confirmed, some are suspected. Some have already disappeared from the record of possibility after better data arrived. That too is part of the journey. The universe is not only discovered, it is corrected. Past Proxima, past Barnard's star, past the faint worlds of Wolf 1061, the stellar neighborhood continues outward into a thinly populated region of small suns and quiet systems. The path between them is wide. The darkness is not a pause between important places. It is the place where most of the journey happens. Beyond the nearby red stars, the journey does not immediately enter emptiness. It enters a neighborhood that is almost invisible. No eye could look out from a spacecraft and see its edges. No window would show a wall of mist, or a river of gas, or the faint boundary between one cloud and the next. Yet the sun is moving through material all the same. Interstellar space is often imagined as a perfect absence, a black interval between stars. It is quieter than any vacuum made on Earth, but it is not clean nothingness. It contains hydrogen, helium, dust grains, ions, magnetic fields, and traces of old stellar deaths spread so thinly that ordinary language struggles to hold them. A handful of atoms in a large volume can still matter when the volume is measured in light years. Across enough distance, even almost nothing becomes an environment. The solar system now moves through what is usually called the Local Interstellar Cloud, or sometimes the local fluff. The name sounds soft, almost domestic, but the thing itself is enormous and faint. It is a warm, partially ionized cloud of gas, part of the very local interstellar medium surrounding the Sunday. Its edges are not sharp. Its shape is not a simple sphere. It is one piece of a larger region where several streams of nearby interstellar gas appear to meet, overlap, and move past one another. Inside the cloud, the temperature can be thousands of degrees, yet there is no heat in the familiar sense. The gas is too sparse. A thermometer placed there would not feel warmth the way it does in air, because there are too few particles striking it. Temperature measures the energy of those particles, not the comfort of the place. This is one of the quiet reversals of space. A gas may be hot and still unable to warm anything. The heliosphere protects the planets from much of this surrounding material, but it does not make the surrounding material irrelevant. The local cloud presses on the sun's outer bubble. Its atoms flow toward the heliosphere, Some neutral particles slip through more easily than charged ones, crossing the boundary and entering the solar system before becoming ionized by sunlight or swept into larger patterns of motion. In this way, the space between stars sends small messengers inward. Those messengers have been measured by spacecraft. They have also been inferred from the light of nearby stars. When starlight passes through thin gas, certain wavelengths are absorbed by atoms along the way. These dark fingerprints reveal what the gas is made of, how fast it is moving, and how it differs from one direction of the sky to another. The cloud around the Sun is therefore known not because it can be seen as a glowing object, but because it leaves faint marks on light and matter. The Sun has not always been inside the same surroundings. As it orbits the Milky Way, it passes through changing regions of interstellar space. Some are thinner, some are denser, some are hotter, some cooler, some shaped by old supernova shocks that expanded through the local galaxy long before human life appeared. The heliosphere changes with these surroundings. If the Sun enters denser gas, the outer bubble may shrink. If the outside pressure weakens, it may expand. Home is moving, and the weather beyond home changes slowly. Around the local interstellar cloud lies the larger local bubble. This is a vast, low-density cavity in the interstellar medium, thought to have been shaped by a series of supernova explosions millions of years ago. The word bubble gives it a harmless sound, but its origin is violent. Massive stars burned through their short lives, collapsed and exploded. Their shock waves pushed gas outward, heated the interior, and left behind a region thinner than much of the surrounding galaxy. The Sun now travels inside this old cavity, through a calm that was made by ancient destruction. The local bubble is not empty either. It contains hot plasma, magnetic structure, and contact zones where it meets neighboring bubbles and clouds. Its walls are not like walls in a room. They are regions where gas becomes denser, where stars may form more easily, where the history of supernovae is written into the shape of the local interstellar medium. The nearby galaxy is not a blank background. It is layered. One of the most delicate clues to this history may lie not in a telescope image, but in Earth's ice. Traces of iron-60, a radioactive isotope that can be produced in supernovae, have been found in deep samples from Earth and from the Moon. Iron-60 does not remain from the birth of the planet in any simple way. Its presence points to material delivered more recently from outside the solar system, tiny grains of interstellar dust, carrying atoms made or scattered by stellar explosions, can drift inward and eventually settle into planetary surfaces. There is something very quiet about that. A star dies somewhere in the nearby galaxy. Its material spreads outward for ages. A few atoms cross the Sun's moving boundary, fall through Earth's atmosphere, and rest in ice. The event is no longer bright. The shock wave is gone. What remains is a trace too small to see, buried in frozen layers, waiting for instruments sensitive enough to count it. The local environment also changes how cosmic rays reach the solar system. These high-energy particles come from outside, from supernova remnants and other energetic processes in the galaxy. The heliosphere helps modulate them, but it does so while moving through interstellar conditions that are not constant. Over long spans of time, the shielding around the solar system may strengthen or weaken depending on the pressure and density outside. This does not mean every cloud crossing becomes a catastrophe. It means the Sun and the galaxy are in contact, and that contact has a long memory. For planets, this wider setting is easy to forget. Earth's atmosphere feels complete from the ground. The sky looks like the boundary of the world. The magnetosphere, the solar wind, the heliosphere, and the local cloud are all hidden layers beyond ordinary sight. Yet each layer belongs to the same nesting of protection and exposure. rock beneath air beneath magnetism, magnetism within solar wind, Solarwind within interstellar gas within the old bubble carved by dead stars. The farther the journey moves from the sun, the more these layers become apparent. The planets are not scattered in a pure void. They are carried through the galaxy inside the remains of stellar events, inside warm clouds, inside flows too thin to see but large enough to shape boundaries measured by spacecraft. Even emptiness has geography here. The local interstellar cloud will not last forever as the sun's surroundings. In a few thousand or perhaps tens of thousands of years, depending on the structure ahead, the solar system may move into another nearby flow or a thinner region within the local bubble. The change will be slow by human standards, almost motionless across generations. For the sun, it is simply travel. For the heliosphere, it is another adjustment of pressure, another reshaping of the invisible shore. Behind that shore, Earth continues through its nights. Above it, stars appear fixed. But the entire system is moving through a vast and faint medium, carrying its planets through the leftovers of older suns. The next darkness is therefore not empty. It is filled with history in its thinnest possible form, and the path outward now leads toward worlds that have left their stars altogether, drifting alone through that same interstellar sea. A world without a star has no morning. There is no first light on the horizon, no slow warming of rock, no season measured by the rising angle of a sun. If such a world turns, it turns through darkness. If it has weather, that weather is not driven by daylight. If it keeps heat, the heat comes from somewhere deeper, older, and less visible. These objects are called rogue planets, free-floating planets, or orphan worlds. The names are not perfect. Rogue can make them sound violent, as if they chose exile. Orphan can make them sound abandoned in a human way. The physical idea is quieter. They are planetary mass bodies not bound to any star, drifting through interstellar space alone, without a host light to reveal them easily. That makes them difficult to find. Most planets are discovered because they affect a star. A planet may dim a star slightly when it crosses in front of it. It may tug the star back and forth with its gravity. It may glow faintly in infrared beside a brighter parent. A free-floating planet has no parent star to dim, no neat system to measure, and often no visible light to give away its position. It can pass through the galaxy like a stone at the bottom of a black sea. The warmest and youngest of them may still shine in infrared, not with reflected starlight, but with leftover heat from formation. In the first part of their lives, large planetary mass objects can be warm enough for sensitive telescopes to detect. Over time, they cool, their glow weakens. The older they are, the more they disappear into the background of space. One nearby object often mentioned in this context is WISE 0855-0714. It is not a simple planet in the usual sense. It is usually classified as a cold brown dwarf or a planetary mass brown dwarf, an object too small to sustain the steady fusion that makes a star shine. Its nature sits near the border where language becomes untidy. It is not a star like the Sunday. It is not a rocky planet like Earth. It is closer in temperature and atmosphere to a giant planet wandering alone without a bright companion. WISE 0855 is only a little more than 7 light-years from the Sunday. That is close in the scale of the galaxy. Yet it cannot be seen in ordinary visible light. It was found through infrared observations because its faint heat betrayed it. Its temperature is near the range of a cold winter on Earth, though its atmosphere and gravity belong to an entirely different kind of body. Observations have shown strong evidence for water clouds or ice in its atmosphere. A lonely object in deep space can still have weather. That detail changes the image. A free-floating world is not necessarily a dead black sphere. It may have clouds. It may have layers of atmosphere, winds, chemistry, and storms too dim for human eyes. On a giant rogue planet, the upper atmosphere may be cold, while deeper layers grow warmer under pressure. Hydrogen can act as insulation. Internal heat can take a very long time to escape. The object may have no sunrise, yet it may not be frozen equally all the way down. There are two main ways such a body might come to exist. In one, it forms inside a planetary system, from a disk of gas and dust around a young star. Early systems are crowded and unstable. Large planets pull on smaller ones. Orbits cross. Close encounters can fling a world outward, giving it enough speed to leave its star behind. The planet becomes unbound because gravity has rearranged the system too violently for every world to remain. In the other path, a small object may form more like a star from the collapse of a gas cloud, but never gather enough mass to ignite sustained fusion. A body with the mass of a planet may not have formed like a planet. A body formed like a star may never become a star. Space does not always respect the categories made for it. The smallest free-floating planets are even harder to understand. An Earth-mass rogue planet would give off almost no light of its own. If it passed near nothing, it would remain unseen. The main way to detect it is gravitational microlensing. For a short time, the planet's gravity bends and magnifies the light of a more distant background star. The event may last only hours or days. Then the alignment ends, and the planet is gone again into darkness. Microlensing is less like seeing the planet than seeing the effect of its weight on light. It gives a temporary signature, a brightening that must be caught at the right time. From that brief curve, astronomers can estimate what kind of object passed in front. The method is powerful because it can find bodies that do not shine. It is also difficult because the opportunity is fleeting. The sky must be watched patiently, again and again, for short changes that may never repeat. Future surveys are expected to find far more of these lonely worlds. Some may be massive, closer to Jupiter or larger. Some may be rocky and smaller. The numbers remain uncertain, but the possibility is wide. Planetary systems may shed worlds during formation more often than once imagined. The galaxy may contain vast populations of planets whose skies have no sun. A rocky rogue planet is a different kind of thought. If it has no atmosphere and no internal heat worth keeping, its surface would become a frozen dark plain, colder than any natural night on Earth. But if it carries a thick atmosphere, especially one rich in hydrogen, that atmosphere could trap heat escaping from within. If it has a deep layer of ice, the ice itself might insulate an ocean below. If radioactive elements inside the rock continue to decay, they may provide slow warmth for billions of years. No sunlight is required for that kind of heat. This does not mean such worlds are likely to be alive. The honest answer is that no one knows. Even if a subsurface ocean exists, life would need chemistry, stability, energy, and time. It would need more than liquid water. It would need a way to build complexity in a place completely cut off from day. The idea is possible enough to matter, but far beyond proof. Still, the existence of such worlds widens the meaning of planet. A planet is not always a companion to a star. It may be a wanderer. It may carry its own heat into the dark. It may spend billions of years between stellar systems, never crossing a sky bright enough to give it noon. If it has moons, they may continue to circle. If it has an ocean, that ocean may never see stars. If it has storms, they may move under clouds, lit only by the faint glow of internal warmth. Most rogue planets will never pass close to the solar system. Most will never be visited, imaged, or named. They will drift through the Milky Way between the brighter points that astronomy usually follows. Their paths may be changed by distant stars, molecular clouds, or the slow gravity of the galaxy itself. Some may one day be captured by a star, though the chance for any single world is small. Others may remain alone until their heat fades into the general cold. The journey outward now feels less like moving from object to object and more like crossing a hidden population. Between the stars there may be worlds without mornings, without constellations fixed to a surface, without a parent sun to define their years. They are difficult to find because darkness suits them, yet they may be everywhere, scattered through the same black sea that the old spacecraft now enter, carrying their private weather through a night that has no horizon. The thought of an ocean usually begins with light, a horizon, a surface touched by wind, a bright path of reflection under a star. But in the outer solar system, water does not always belong to daylight. Sometimes an ocean is hidden under ice, under pressure, under a sky that never warms it. Europa is one of the places that changed this idea. From far away, it is only one of Jupiter's moons, a pale world scored by dark lines. Up close, its surface looks fractured, shifted, and repaired, as if the icy shell has been stressed again and again from below. The moon is not warmed mostly by sunlight. Jupiter is too far from the sun for that. Instead, Europa is pulled by gravity. As it moves around Jupiter, the giant planet and nearby moons flex it slightly, deforming its interior and creating heat through tidal forces. That heat may help keep a global ocean beneath the ice. The surface stays frozen, but the deep interior does not have to follow the surface. Pressure changes the behavior of ice. Salts and chemistry alter the freezing point. A rocky seafloor below the ocean may interact with water in ways that matter for habitability. Europa is therefore not interesting because it looks alive. It is interesting because it is dark, cold, and still physically able to hold liquid water. Enceladus carries the idea. It is smaller than Europa, a bright, icy moon of Saturn, and from a distance it looks too delicate to hide a deep interior. Yet Cassini found plumes rising from cracks near its south pole. Those plumes carried water vapor, ice grains, salts, organic molecules, and signs of chemistry from below. The moon was not silent. It was venting material from an ocean into space. Cassini measurements showed that Enceladus has a global ocean beneath its crust. Later, evidence pointed toward water interacting with rock at the ocean floor, producing hydrogen. On Earth, hydrogen from hydrothermal systems can serve as chemical energy for microbes. The connection must be handled carefully. Enceladus is not Earth, and chemical energy is not life. But it shows that sunlight is not the only possible engine for an ocean world. Deep under Earth's own oceans, far from the surface, life gathers around hydrothermal vents. There, darkness is complete. Sunlight does not reach. The energy comes from chemistry, from hot fluids moving through rock and returning to cold seawater, loaded with minerals. Microbes use chemical gradients instead of daylight, and larger ecosystems build around them. This does not prove that life exists under Europa or Enceladus. It only removes one old assumption. Biology, at least on Earth, can live without noon. That matters for rogue planets. A planet, drifting alone between stars, would have no sunlight to feed a surface ecosystem. Photosynthesis, in the familiar sense, would not shape the world. There would be no green continents under a blue sky. Yet if the planet is rocky, if it has enough water, and if it keeps a thick layer of ice above that water, the ice may become a lid. It would not merely be a prison of cold, it could also be insulation, slowing the loss of internal heat into space. The heat inside a rocky planet has several sources. Some is left over from formation, from the violence of accretion and differentiation when heavy material sank inward and lighter material rose. Some comes from radioactive elements decaying slowly over time. If the planet has a large moon, or if it was thrown out of its system while still retaining moons, tidal forces might add more heat by flexing its interior. None of these sources is as bright as a star. They are quiet, they are patient, they work from below. Under enough ice, pressure may keep water liquid, even when the surface is far below freezing. The ocean would not have waves in the ordinary sense. It would not smell of salt air. It would not reflect a sky. It might lie between a frozen crust above and rock below, completely enclosed, with currents driven by heat escaping from the interior. Minerals could dissolve from the seafloor. Chemistry could move slowly through darkness. A hydrogen atmosphere could change the picture too. Hydrogen is light and difficult for a small planet to hold close to a star, but a free-floating planet far from stellar radiation might retain it more easily. A thick hydrogen envelope can trap heat efficiently. In some models, a rogue planet with such an atmosphere could maintain surface or near-surface liquid water even without sunlight. The atmosphere would act like a deep blanket wrapped around a world that has no day. The image is strange because it breaks the usual language of habitability. A habitable world is often pictured as Earth seen from space, blue, clouded, and bright. But habitability is not beauty. It is not comfort. It is a set of physical and chemical permissions. Liquid water may exist in darkness. Energy may come from rock. Stable conditions may persist under ice rather than under an open sky. There are limits. An isolated planet can lose heat over time. Its radioactive elements decay away. Its ocean, if it has one, may freeze from above and below. Without active rock-water interaction, the chemistry needed to support metabolism might become poor. Without a steady source of energy, liquid water alone would be a closed room. The difference between a hidden ocean and a living ocean may be very large. No telescope can yet confirm such an ocean on a rogue planet. There is no direct image of black water under alien ice between the stars. The argument is built from physics, from known ocean worlds in the solar system, from models of atmosphere and heat flow, and from the fact that planets are more varied than the old picture allowed. It is a cautious possibility, not a discovery. Even so, the possibility changes the feeling of interstellar darkness. The spaces between stars may not be filled only with frozen debris and silent stones. Some bodies may carry interiors warmer than their surfaces suggest. Some may hide liquid layers under pressure. Some may have moons locked in private orbits, producing faint tides in a system with no sun. Their calendars would not be made from seasons. Their history would be written in cooling rates, fractures, minerals, and the slow movement of heat. If life ever began in such a place, it would be difficult to imagine from the surface. There might be no surface life at all. No color, no plants, no animals rising through water lit from above. At most, one can speak of simple chemistry, microbial possibilities, and ecosystems whose energy would have to come from the meeting of water and rock. Any such life would be hidden twice. First by ice, then by distance. This is why the idea remains both modest and large. It does not claim that the galaxy is filled with living rogue planets. It only says that darkness does not automatically close every door. The absence of a star removes one source of energy, but not all sources. The absence of morning does not erase the interior of a world. Out beyond the last influence of familiar sunlight, a rogue planet may drift for billions of years, wearing a crust of frozen night. Beneath that crust, if conditions were kind in the narrow way physics allows, water might remain. It would be an ocean without storms under a sky, without dawn, a hidden sea. moving slowly in the dark, carrying whatever chemistry time has left inside it. The journey through such worlds is a journey through what cannot yet be seen. The galaxy shows its stars first, because stars are generous with light. Planets without stars must be known indirectly, through brief lensing events, faint heat, or future instruments not yet fully tested by the sky. Their oceans, if they exist, are even deeper in the unseen, yet the thought of them lingers, because it makes the interstellar dark less empty without making it less quiet. A black hole does not need to move through space like a predator. It does not sweep the galaxy clean. It does not reach across the dark and pull every nearby star into itself. From far enough away, its gravity behaves like the gravity of anything else with the same mass. A planet can orbit. A star can pass by. Light can move through the surrounding space without falling. So long as its path does not come too close, the difference begins near the center. A black hole is not powerful because it is large in the ordinary sense. Many stellar black holes are smaller across than a city, yet contain several times the mass of the Sunday. Their strangeness comes from compression. Matter has collapsed into a region so dense that a boundary forms around it, a place from which light itself cannot escape. That boundary is called the event horizon. It is not a surface made of material. It is a limit in space-time, a point of no return for anything that crosses inward. Outside that boundary, the universe still has rules. Gravity curves paths. Objects orbit if their speed and distance allow it. Gas can circle. Stars can move around a dark companion for millions of years. A black hole may be invisible by itself, but the space around it can become bright when matter is forced into motion. One of the closest known examples is A0620-00, also known as V616 Monocerotis. It lies thousands of light-years away, close by galactic standards but far beyond any human reach. The system contains a dark, compact object and a smaller companion star. The companion is not massive, it is a cool, ordinary star, pulled into an orbit so tight that a complete circuit takes less than a single Earth day. The black hole itself is not seen as a glowing sphere. It does not have a surface to shine. Its presence is inferred from the way the companion star moves, from the mass required to explain that motion, and from the light produced by matter near the invisible object. The dark body is too heavy to be a white dwarf. It is too heavy to be a neutron star in any usual sense. What remains is a black hole. The companion star does not fall straight in. That is important. It orbits, but the orbit is close enough, and the gravity strong enough, that the star is distorted. It becomes slightly stretched, no longer a perfect sphere. Its outer layers are drawn toward a gravitational balance point, where matter can begin to spill away. Gas leaves the star and moves toward the black hole, not as a clean stream into darkness, but as a rotating flow. That flow becomes an accretion disk. An accretion disk is one of the great ironies of black holes. The black hole is dark, but the material around it may become intensely bright. Gas in the disk orbits at high speed. Inner layers move faster than outer layers. Friction, turbulence, and magnetic effects heat the material until it radiates. The light does not come from inside the event horizon. It comes from matter still outside. Matter that has not yet crossed the final boundary. In systems like A0620-00, the disk can be faint for long periods, then brighten during outbursts when more material moves inward. The system may sleep in a quiet state, with only traces of activity, then briefly reveal the violence of its inner structure. Even then, the black hole itself remains unseen. Only its surroundings speak. The idea of falling into a black hole is often pictured as a sudden drop. In reality, for matter outside the horizon, the story can be slow and orbital. Gas may circle again and again, losing energy, moving inward by degrees. Magnetic fields thread the flow, heat rises, radiation escapes. Some material may be driven away in winds or jets rather than swallowed. A black hole can feed, but feeding is not simple. It is a process of motion, heating, loss, and only then disappearance. Tidal forces decide much of the shape of that process. Gravity is stronger on the near side of an object than on the far side. Near a compact object, the difference can be large enough to stretch a star, pull gas from it, or tear smaller bodies apart. The same basic idea raises tides in Earth's oceans because the moon pulls more strongly on the nearer side of the planet. Around a black hole, the scale is changed until the effect becomes able to reshape stars. A planet passing too close could be destroyed. Its near side would feel a stronger pull than its far side. Rock, ocean, atmosphere, and mantle would not all respond together. The world could be stretched, fractured, heated, and eventually torn into streams of debris. Those streams might wrap around the black hole, collide with themselves, and join a disk of glowing matter. A planet would not vanish in one theatrical instant. It would become part of a changing flow. Farther away, a planet could survive. This is the quieter counterpoint. If the orbit is stable and the radiation environment is not too severe, a planet can move around a black hole in the same mathematical sense that it moves around a star. Gravity does not care whether the central mass shines. The orbit cares about mass, distance, speed, and disturbances from other bodies. In principle, there could be planetary systems around black holes. How would such planets form? One path begins after a massive star dies. A supernova can leave behind a black hole and scatter heavy elements into space. Some of the ejected material may remain bound, forming a disk from which later bodies might grow. This is not guaranteed. The explosion is violent, and much of the material escapes. But under some conditions, dust and gas around compact remnants can become the raw material for new objects. Another path is capture. A black hole moving through a dense region of stars might pass close enough to disrupt an existing planetary system. Some planets would be ejected, some would be swallowed. A few, under rare circumstances, might settle into new orbits around the black hole or around a surviving companion star. The system, after such an encounter, would not look gentle. It would be a rearranged architecture, built from loss. A third path is inheritance. If a star with planets becomes a black hole, some outer planets might survive the transformation, provided they are far enough away and the mass loss does not unbind them completely. Their skies would change beyond recognition. The star that once gave them daylight would be gone or transformed. If an accretion disk formed, it might become a harsh substitute sun, bright in dangerous wavelengths and unstable over time. The planets would orbit a dark center, warmed only if the surrounding matter happened to shine. Habitability around black holes is therefore not impossible in the language of physics, but it is difficult in the language of conditions. Radiation from a feeding disk can be destructive. A quiet black hole provides no sunlight. Nearby stars may disturb orbits. Tidal forces may become dangerous. Stable does not mean comfortable. A world can move safely around a black hole and still be lifeless, frozen, irradiated, or stripped. The black hole at the center of the Milky Way shows another scale entirely. Sagittarius. A star holds millions of solar masses in a compact central region, but Earth is safe because distance matters. The solar system orbits the galaxy far away, not because the central black hole drags it directly like a hook, but because the whole mass of the galaxy shapes the motion of stars. The central darkness is important, but it is not the only gravity in the Milky Way. This is where the common image softens. Black holes are not mouths roaming through the universe. They are places where gravity has made escape impossible past a boundary. Around them, matter can orbit, shine, heat, tear, or survive depending on distance and motion. They are dark, only at the center. Their surroundings can be among the brightest regions in space. A 0620-00 remains quiet in the telescope's view much of the time, a faint system in Monoceros, carrying a dark object and a damaged companion around a shared center of mass. Nothing about it is theatrical from Earth. Its light is weak. Its changes are subtle. Yet within that faintness, a star is slowly losing material to something that cannot shine, and the lost gas briefly becomes visible before crossing into a region from which no message returns. Out past the rogue worlds, past the frozen oceans that may never see a sky, black holes mark another kind of darkness. Not empty darkness, gravitational darkness, a darkness with structure, with disks, with orbits, with mathematics written into the paths of stars. The journey through deep space does not stop at them. It bends around them, learning that even the blackest places in the universe are not simple absence, but hidden mass shaping the light around it. The Milky Way is easiest to see from inside it as a pale river. On a dark night, far from city light, it crosses the sky like spilled frost, soft enough to seem almost atmospheric. It looks near because it belongs to the sky. It looks simple because the eye cannot separate its parts. But the glow is not a cloud above Earth. It is the combined light of stars, so numerous and distant that they blur into one another, and the darker lanes across it are not gaps in the galaxy, but dust hiding what lies beyond. To look toward the center of the Milky Way is to look through a crowded and obscured road. The galaxy does not show its heart plainly. Between Earth and the central region are enormous clouds of interstellar dust, grains small enough to drift between stars, and thick enough in total to block visible light. The center is bright, but much of that brightness is covered. It is not absent. It is veiled. This is why the Milky Way had to be mapped in more than ordinary starlight. Radio waves pass through dust more easily. Infrared light can slip through regions that visible light cannot. X-rays reveal energetic places where gas is heated, stars explode, or matter moves near compact objects. The galaxy beneath the dust is not the same galaxy the eye sees. It has a hidden architecture, and every wavelength opens a different corridor. Near the center lies Sagittarius A star, the compact radio source associated with the Milky Way's central supermassive black hole. Around it, stars move in tight, swift orbits. Their paths have been followed for years, and from those motions, astronomers infer the mass gathered in the center. Roughly 4 million times the mass of the Sun, packed into a region far smaller than any ordinary star cluster could explain. The black hole itself does not shine, but the behavior of the stars around it gives away its presence. In the year 2022, the Event Horizon Telescope released the first image of Sagittarius A star's immediate surroundings. The image was not a photograph in the everyday sense. It was the result of radio telescopes spread across Earth, working together as one planet-sized instrument. What appeared was a bright ring of emission around a darker center, light from hot gas shaped by gravity near the event horizon. The picture did not make the black hole familiar. It made the evidence visible in a new way. Sagittarius A star is quiet compared with many supermassive black holes. It is not feeding at the rate of a quasar. It does not blaze across the universe from billions of light years away. Yet quiet does not mean inactive. Gas and dust still move near it. Flares rise and fade. Stars pass through its neighborhood at speeds that make ordinary orbital motion seem slow. Close to the center, gravity is not a background condition. It is the shape of the place. The surrounding region is not empty around the black hole. It is crowded with stars, many of them young and massive, a fact that once seemed difficult to explain. Strong tidal forces near the central black hole should make star formation harder, because gas clouds can be pulled apart before they collapse. Yet stars are there. Some may have formed in dense disks of gas able to resist disruption. Some may have migrated inward. The details remain an active problem, but the view is clear enough. The galactic center is both destructive and creative. Farther out from the central black hole lies the central molecular zone, a broad region rich in dense gas. It contains clouds with masses far beyond anything in the local neighborhood of the Sunday. Within those clouds are molecules that speak of cold chemistry and future stars. Hydrogen, carbon monoxide, methanol, hydrogen cyanide, and more complex traces mixed into the dark. The gas is not evenly spread. It forms arcs, filaments, clumps, and turbulent streams. Some parts of this zone are stellar nurseries. Others are strangely inefficient, holding large amounts of dense gas without forming stars as quickly as expected. Motion, magnetic fields, turbulence, and radiation all shape what the gas can do. A cloud may contain enough material for many stars and still wait. Unstable, but not yet collapsing. The galaxy does not turn gas into light at the same pace everywhere. The bulge surrounds the central region, a thick swelling of older stars around the heart of the Milky Way. From outside the galaxy, it would appear as a bright central structure, but from Earth, the dust lanes make it difficult to see cleanly. Within the bulge, stars move in many directions, bound by the combined gravity of the central mass, the bar, the disk, and the dark matter surrounding all of it. The Milky Way is a barred spiral galaxy. Its central bar is a long structure of stars crossing the inner disk, and from its ends, the spiral arms begin their wider curves. The Sun is not in one of the great central regions. It sits in a smaller arm or spur, far from the crowded core, about 27,000 light-years from the center. This distance matters. The local sky is calmer than the inner galaxy, with fewer nearby massive stars and less radiation from the central regions. Between the Sun and the center lies the Great Rift, the dark band visible across the Milky Way's glow. It is not an absence of stars. It is dust. Huge molecular clouds block the light behind them, making parts of the galaxy appear split and hollow. To the naked eye, the rift looks like a tear in the celestial river. In physical terms, it is cold interstellar material, rich with gas and dust, capable of hiding millions of stars from visible view. Dust is often treated like an obstacle, something to see through, but it is also part of the galaxy's life. Dust grains help shield molecules from harsh radiation. They provide surfaces where chemistry can occur. They cool gas by radiating energy away, allowing clouds to collapse more easily under gravity. Without dust, the galaxy would be more transparent, but not necessarily more fertile. The same material that hides stars also helps make new ones. Beyond the visible disk lies the halo. The bright disk gives the Milky Way its familiar shape, but the halo makes the galaxy larger and older than the disk alone suggests. It contains globular clusters, ancient groups of stars packed into dense spheres. Many of their stars formed early in the history of the galaxy, and their low amounts of heavy elements preserve a chemical memory of a younger universe. The halo also contains stellar streams, long trails of stars pulled from smaller galaxies and clusters by the Milky Way's gravity. These streams are faint, but they are records of past encounters. A dwarf galaxy approaches. The Milky Way's tidal forces stretch it. Stars peel away and wrap around the larger galaxy, leaving a trail that can persist long after the original system has nearly dissolved. Much farther out is the dark halo. the unseen mass inferred from the motions of stars, gas, and satellite galaxies. The visible Milky Way does not contain enough matter to explain how the galaxy rotates and holds together. Something else contributes gravity. It does not shine in any ordinary way. It does not form stars. It reveals itself by motion. Dark matter is not a decorative addition to the galaxy. It is part of the reason the disk can exist as it does. From inside, the view is partial and intimate. The galaxy is both shelter and obstruction, both map and fog. It holds the sun in a quiet outer region, carries ancient ruins in its halo, feeds stars in its dusty arms, and hides its heart behind a veil of cold grains. The journey has not left home behind completely. It has only made home larger, darker, and more difficult to see. The halo of a galaxy is not the part that first catches the eye. The disk has the arms, the center has the crowded light, the dust lanes have shape and contrast. The halo is fainter, wider, and older, a loose surrounding volume where stars move on tilted paths. Globular clusters drift like ancient islands, and long streams of lost suns arc through space almost too dim to notice. From inside the Milky Way, the halo is difficult to feel. Earth sits in the disk, surrounded by the flattened structure where most of the gas, dust, and young stars are found. The halo rises above and below that disk, not as a roof, but as a great sparse envelope around the galaxy. Its stars are fewer. Many are old. Their orbits often do not follow the calm rotation of the sun and its neighbors. Some plunge inward and outward. Some move against the general flow. Some carry chemical signatures unlike the stars born quietly in the Milky Way's own disk. Those differences are clues. A star keeps a memory of where it came from in more than one way. Its motion is one memory. Its chemistry is another. Stars born from the same cloud of gas tend to share certain chemical patterns because the cloud was already enriched by earlier generations of stars. A star with fewer heavy elements may have formed in a smaller, older system where star formation was slower. A star moving on a stretched orbit may have been thrown into the Milky Way during an ancient collision. The star does not tell the story in words. It tells it by moving. For a long time, these memories were difficult to read. A few nearby stars could be measured carefully. Larger patterns remained blurred. Then Gaia began mapping the positions, motions, and distances of enormous numbers of stars with a precision that changed the study of the Milky Way. Groups of stars that looked unrelated in the sky were found to share motion. The halo became less like a vague sphere and more like a record of events. One of those events was the merger with the galaxy now called Gaia Enceladus, also known in some studies as the Gaia sausage because of the stretched shape of its stars in velocity space. Around 10 billion years ago, the young Milky Way collided and merged with a smaller galaxy. The smaller system did not survive as a separate galaxy. Its stars were scattered into the Milky Way, many of them placed on long radial orbits that carry them toward the center and back out again. They became part of the stellar halo. This was not a minor disturbance. The merger likely helped heat the early disk of the Milky Way, making stellar orbits thicker and less orderly. It may have contributed to the formation of the thick disk, a component older and puffier than the thin disk, where the sun now lives. A galaxy can look settled today and still carry the motions of an event that shook it before Earth existed, before the sun existed, before the familiar spiral pattern took its later form. The name Gaia Enceladus can sound like a label placed on something distant and complete. In reality, the object itself is gone. There is no small galaxy still visible with a clear outline, no bright core left intact in the sky. What remains is debris, not debris like broken stone, but stars still shining after their parent system was torn apart. Each star continues its own orbit, yet together they preserve the shape of an old collision. The Milky Way has done this more than once. The Sagittarius dwarf galaxy is being pulled apart even now. It passes around the Milky Way on a large orbit, and each passage strips stars from it. Those stars form the Sagittarius stream, a long arc wrapping around the galaxy. It is not a stream of gas or dust in the usual sense. It is a stream of stars, stretched by tidal forces until the original galaxy becomes less like a separate companion and more like a trail. The stream crosses great distances above and below the disk, tracing the invisible pull of the Milky Way's mass. Such streams are useful because they are sensitive to gravity. A stream does not move only through the visible galaxy. It feels the dark halo as well. If the halo is round, flattened, lopsided, or disturbed, the path of the stream changes. The stars become test particles in the largest gravitational experiment available, moving through a field that cannot be seen directly. Globular clusters belong to this older story too. Dense systems of ancient stars, some native to the Milky Way, others perhaps captured from smaller galaxies. In the halo, even a cluster can be a fossil. The word fossil fits only if it is used gently. A stellar fossil is not dead. It shines. It moves. What is fossilized is not the star itself, but the event preserved in its motion, age, and chemical pattern. The Milky Way's halo is filled with living remnants of vanished systems. This changes the meaning of a galaxy. A galaxy is not a single object assembled once and left alone. Smaller galaxies fall in. Some are stretched into streams. Some sink deeper and vanish into the central regions. Gas arrives and fuels new stars. Dark matter shapes the larger field. The disk settles, then is heated. The halo grows by accumulation. Time does not simply pass over a galaxy. It builds the galaxy in layers. The Sun formed long after the Gaia-Enceladus merger. Its birthplace was in the disk, enriched by many generations of older stars. Yet the Sun's galaxy still carries the older impact. Somewhere above and below the disk, stars from that lost galaxy continue to swing through the halo. They do not belong to the same origin as the Sun, but they now belong to the same Milky Way. There is a quiet kind of violence in this. The stars themselves do not collide. Space between them is too wide. When galaxies merge, their gas clouds may crash, their shapes may twist, their dark halos may combine, and their stars may be thrown into new orbits. But individual stars mostly pass through the encounter without touching. Gravity does the work at a distance. That distance is why the evidence lasts. A collision between galaxies is not over when the bright disturbance fades. It can leave streams, shells, warped disks, thickened structures, and chemical fingerprints that remain for billions of years. The present shape of the Milky Way is therefore a calm surface over older motion. Under the familiar band of light, there are older paths crossing at angles, the remnants of places that no longer have names beyond the names astronomers give their debris. The journey outward from the center now passes through this faint memory field. The bright disk falls behind. The arms become less dominant. The halo opens into a sparse volume where ancient clusters and stolen stars move through the dark. Some of them were born in the Milky Way. Some were born elsewhere and arrived through collision. All of them now trace the same larger gravity. Beyond the halo, the Milky Way is not alone. Nearby dwarf galaxies still orbit. Some will survive for a time. Some will be pulled apart, farther away. Andromeda approaches on a slow path that will one day change both great spirals. The fossil streams of the present are not only relics of what has ended, they are previews of what galaxies do over long enough time. The Milky Way carries its past around it like a dim, outer atmosphere of stars. It is easy to miss because it is so faint, and because the eye prefers the bright river of the disk. But the halo is where the galaxy's memory becomes visible, not as a written archive, but as motion. Stars from vanished systems continue their long orbits in silence, held inside a gravity larger than the light can show. Andromeda approaches quietly in the northern sky. To the unaided eye, under dark conditions, it is only a soft, elongated patch, a small cloud of light that seems almost fragile. It does not look like a galaxy large enough to hold hundreds of billions of stars. It does not look like the nearest great spiral neighbor of the Milky Way. It looks like breath on glass. For centuries, that softness shaped how it was understood. Before distances to galaxies could be measured, the Andromeda object was often placed within the Milky Way, treated as a nebula, a cloudy region of light, among other cloudy regions. It had a name, a position, and a visible shape, but not yet its true scale. The universe was still small in human measurement, even though it had always been large. Then came the slow correction. Better telescopes resolved more detail. Variable stars were measured. The distance grew in the mathematics, until Andromeda could no longer fit inside the Milky Way. It was not a nearby mist. It was another galaxy, separated by millions of light-years, carrying its own disk, its own dust lanes, its own clusters, its own old stars and new stars. The soft patch became an island universe. Long before that correction was complete, Andromeda gave astronomers a flare they could not properly place. In 1885, a bright new point appeared near its center. It was S Andromedae, a supernova seen in a galaxy whose true nature was not yet widely accepted. The light had crossed intergalactic space for more than 2 million years before entering telescopes on Earth. The star had already died, long before any human recorded it. What was seen was not a present event, but an arrival. That is one of the gentlest and strangest facts of astronomy. A catastrophe can become a quiet dot. A star can be destroyed with enough energy to outshine much of its surroundings. And by the time its light reaches another world, it may look like a small temporary brightening in an eyepiece. The violence belongs to the source. The stillness belongs to the observer. The remnant of S Andromedae was difficult to identify for many years because the explosion occurred near the bright central region of the galaxy. Andromeda's nucleus is crowded and luminous, a place where starlight blends into a dense glow. Only much later was a small remnant detected against that background. The old supernova became not only an event in a record book, but a physical trace inside another galaxy. The center of Andromeda is stranger still. Hubble observations revealed that the nucleus of Andromeda is double, or at least appears as two concentrated peaks of light. One peak is brighter and slightly offset. The other is dimmer and closer to the true dynamical center, where the central black hole lies. At first glance, this might sound like two separate nuclei, as if two galactic hearts had survived side by side. The deeper explanation is subtler. The double structure is now often understood as an eccentric disk of old red stars orbiting the central black hole. In such a disk, stars do not form a perfect circular ring around the center. Their orbits are stretched, and they spend more time near one side of their paths, making one region appear brighter. What looks like a second nucleus may be a crowding of stars in a lopsided orbit, a gravitational pattern mistaken at first for a separate core. Near the true center is also a compact cluster of blue stars. These stars are young compared with the old red stars surrounding them, and their presence near a supermassive black hole raises its own quiet questions. Star formation close to such gravity is difficult. Gas must become dense enough to collapse while resisting tidal disruption. Yet the stars are there, moving near a black hole whose mass is often estimated at tens of millions to around 100 million times the mass of the Sun, depending on the method and model used. The event horizon of that black hole is far too small to see from Earth. What can be studied are the stars and gas around it, the light from the central region, and occasional high-energy behavior. Like Sagittarius A star in the Milky Way, Andromeda's central black hole is not a quasar. It is not feeding with enough force to blaze across the universe. It is comparatively quiet, which makes it less dramatic and more difficult. Quiet objects keep their secrets longer. Around the core, Andromeda's bulge swells with older stars. The bulge is large, bright, and dense, giving the galaxy its luminous center. Beyond it lies a disk marked by dust lanes and spiral arms. In photographs, those lanes curve like dark smoke around the central glow. They are not empty spaces. They are cold material blocking light, mixed with gas that can feed star formation where conditions allow. In the arms, young blue stars appear with nebulae and open clusters. One of the most prominent stellar associations is NGC 206, a vast region of hot young stars in Andromeda's disk. Its stars shine blue-white, short-lived compared with the older population of the bulge. They are reminders that Andromeda is not merely an old neighbor waiting in silence. It still forms stars, though not with the same intensity as the most active galaxies. Andromeda also carries signs of past encounters. Its halo contains streams and substructures, evidence that smaller galaxies have been pulled apart and absorbed. M32 and M110, its well-known companions, are not just decorations around a larger spiral. They are part of a gravitational environment in which galaxies disturb, strip, and reshape one another across long spans of time. Andromeda has grown by taking in smaller systems, just as the Milky Way has done. This makes the two great spirals feel less like isolated islands and more like histories still in motion. The Milky Way carries Gaia Enceladus in its halo. Andromeda carries its own accreted debris, its double central structure, its satellite galaxies, its old supernova remnant near the glow of the core. Each galaxy is a present shape made from earlier collisions. Andromeda is also approaching, not in a sudden way, not as a threat to any single night sky now. Its motion toward the Milky Way unfolds across billions of years. In the far future, the two galaxies are expected to merge, their stars mostly passing between one another because the distances between stars are so wide. Gas clouds may collide. New star formation may be triggered. The disks may lose their present spiral shapes. A larger, more elliptical galaxy may eventually remain. By then, the Sun itself will be far older. Earth, if it still exists in any recognizable form, will not be the world it is now. Galactic time does not wait for human categories. It carries stars, dust, black holes, and dark matter through encounters so slow they can look motionless from within a single lifetime. For now, Andromeda remains a pale patch in the sky and a vast system in space. Its light left before modern humans existed. Its central black hole sits hidden inside a double-looking heart. Its old supernova remnant rests near the bright core like a cooled ember. Its arms continue to hold young blue stars. Its halo remembers smaller galaxies. And all of it is moving, slowly, toward the Milky Way. The journey outward has crossed from one galactic memory to another. The Milky Way is no longer the only home-shaped structure in the dark. Ahead and beside it, Andromeda carries a second history, close enough to see without a telescope, distant enough that its light arrives as ancient news. Beyond the halo of the Milky Way, the galaxy does not end into loneliness at once. It becomes part of a small gathering. The stars thin out, the streams become faint, the dwarf companions grow more separate, and then the larger shape appears. a local family of galaxies held together by gravity in the expanding universe. This family is called the Local Group. Its largest members are the Milky Way and Andromeda. Triangulum is smaller, but still a major spiral in the same neighborhood. Around them move dozens of dwarf galaxies, some bright enough to have names familiar to astronomy, many faint enough to be found only by careful surveys. The group is not crowded in the way a star cluster is crowded. The distances between galaxies are wide, measured in hundreds of thousands or millions of light years. Yet gravity still links them. The local group is not a set of islands floating without motion. It is more like a slow system of tides. Dwarf galaxies orbit larger ones. Some are stretched by tidal forces. Some lose gas. Some stop forming stars after their fuel is stripped or heated. Some may already be remnants, their original shapes softened by repeated passages around a more massive neighbor. Even in a quiet local group, galaxies are not simply placed in space. They are being changed by where they are. The Magellanic Clouds, visible from Earth's southern skies, are part of this story. They are satellite galaxies of the Milky Way, rich in gas, bright with star-forming regions, and linked to long trails of hydrogen pulled through space. The large Magellanic Cloud is massive enough that it does not merely orbit as a passive companion. It affects the Milky Way too, tugging on the outer disk and dark halo as it moves. A small galaxy can still matter when its mass is large enough and its path is close enough. Andromeda has companions of its own. M32 and M110 lie near it in the sky. Small compared with the Great Spiral, but important in the history of its structure. Around Andromeda, streams and satellite systems show that the large galaxy has fed on smaller ones, gathering stars and reshaping its halo. The same kind of evidence surrounds the Milky Way. The local group is therefore not only a neighborhood, it is a record of eating, stripping, falling, and survival. Triangulum, or M33, sits between the scale of the great spirals and the smaller dwarfs. It is a spiral galaxy with open arms, active star-forming regions, and a less dominant central bulge than the Milky Way or Andromeda. It may be gravitationally linked to Andromeda in a long history of interaction, or at least shaped by the same larger environment. In the future, its path will matter in the changing relationship between the largest local galaxies. The distances are large enough that the word group can feel misleading. Light from Andromeda takes more than 2 million years to arrive. Light from Triangulum takes even longer. The space between these galaxies is not filled with familiar scenery. There are no continuous bridges of stars bright enough for the eye. There is darkness, thin gas, faint streams, dark matter, and the slow pull of mass across distances where a galaxy can appear as only a haze. Farther out, the local group belongs to larger structures, sheets, filaments, and clusters. Galaxies are not scattered randomly across the universe. They gather along the cosmic web, the large-scale pattern shaped by gravity, pulling matter into walls and strands, while leaving broad voids between them. On this scale, galaxies become less like isolated objects and more like bright knots in a dark net. In richer galaxy clusters, the environment becomes harsher. A galaxy moving through a cluster does not travel through emptiness alone. The cluster contains a hot, thin plasma spread between its galaxies. This intracluster medium is far more rarefied than air, but a galaxy moving through it at high speed can feel it as pressure. The effect is called ram pressure stripping. Gas is pushed out of the galaxy, trailing behind like material blown by a headwind. ESO 137-001 shows this process clearly. It is a spiral galaxy falling through the Norma cluster, leaving behind long streams of gas and young stars. In images combining visible and X-ray observations, it resembles a jellyfish, with blue trails extending from the disk. The stars already formed inside the galaxy mostly continue moving along their orbits, but gas is more easily stripped. Without gas, future star formation becomes harder. The galaxy is being altered, not by a direct collision with another galaxy, but by the medium through which it moves. This is one of the quiet lessons of clusters. Space between galaxies can shape galaxies. A substance too thin to see with ordinary eyes can remove the raw material for future stars. The galaxy keeps its old stellar body for a while, but its ability to renew itself is weakened. It becomes a system losing its future, one stream at a time. Other galaxies carry signs of different histories. The Sombrero Galaxy, Messier 104, lies far beyond the local group, seen nearly edge-on with a dark ring of dust cutting across its bright central bulge. The shape gives it its familiar name, but the structure is more than appearance. The dust ring marks a flattened disk wrapped around a large central concentration of stars. The galaxy has traits that make it difficult to place into a simple category. It is not only one kind of thing in the easy language of shapes. It carries a bright bulge, a striking disk, and a massive central object. Messier 64, the Black Eye Galaxy, holds another kind of memory. Its dark dust band partly covers its bright center, giving it the appearance that made its name. But the stranger feature is motion. Gas in the outer regions rotates in the opposite direction from the gas and stars closer in. Such counter-rotation may come from a past merger or from gas acquired from another system. The dark band is visible. The deeper story is dynamic. A galaxy can wear the mark of something it swallowed, not only in its shape, but in the direction its gas moves. M86 in the Virgo cluster offers another slow scene of motion. Unlike many distant galaxies carried away by cosmic expansion, it is moving through its cluster environment in a way that brings its light toward the blue side of the spectrum. It is surrounded by signs of interaction with hot gas and nearby galaxies. In a cluster, even a large galaxy is not alone. Its gas, halo, and motion are shaped by the gravitational field of the whole system. The pattern repeats at different scales. Dwarf galaxies around the Milky Way lose stars to tidal streams. Spirals in clusters lose gas to pressure. Galaxies like Messier 64 preserve the odd motion of acquired material. The Sombrero Galaxy holds a bright bulge and dark ring that speak of a layered past. None of them are frozen portraits. A telescope image stops the motion for the eye, but the systems themselves are moving, rotating, falling, feeding, and changing. Between them lies the empty sea. It is not truly empty, just as interstellar space is not truly empty. There is gas too thin to feel, dust too sparse to see, magnetic fields, dark matter, wandering stars, and light traveling from old events toward future observers. But compared with a galaxy, the space between galaxies is a silence of scale. Most of the volume belongs to the gaps. The journey outward from Andromeda therefore becomes a change in proportion. Galaxies that once filled the story begin to shrink into islands. Their disks become ovals and smudges. Their histories become faint structures in a wider web. The bright matter gathers in knots, while the darkness between them widens. Gravity still connects the scene, but it does so across distances that make even the Milky Way feel small. Past the local group, past the neighboring clusters, and the strange galaxies shaped by pressure and merger, the universe begins to reveal its larger pattern. It is not a random scatter of lights. It is a web with threads, walls, intersections, and broad spaces where very little gathers. The next part of the journey moves toward those spaces, where the brightest structures fall behind and the voids begin. The farther the journey moves from the islands of galaxies, the more the universe begins to look less like a collection of objects and more like a pattern. Galaxies do not fill space evenly. They gather, They thread themselves into filaments, sheets, knots, and walls, leaving broad regions between them where very little luminous matter gathers. From far enough away, the cosmos resembles a web drawn in faint light, with most of its volume held in the dark spaces between the strands. These dark spaces are called cosmic voids. The name is simple, but it can mislead. A void is not absolute nothingness. It may contain faint galaxies, thin gas, dark matter, radiation passing through, and particles too sparse to make a visible structure. It is empty only by comparison. Beside a galaxy cluster, where hundreds or thousands of galaxies gather in a deep gravitational well, a void is an underdense region, a place where matter did not collect as strongly while the universe grew older. The origin of voids begins in the early universe, before galaxies, before stars, before any dust had formed around dying suns. The young cosmos was almost smooth, but not perfectly smooth. Tiny differences in density were present in the hot early matter and radiation. Gravity took those small differences seriously. Regions with slightly more matter pulled in more. Regions with slightly less matter lost material to their surroundings. Over billions of years, the denser places became filaments and clusters, while the thinner places opened into voids. In this sense, a void is not an accident. It is part of the same structure that made galaxies. The web and the emptiness grow together. Matter flows away from underdense regions and toward the denser boundaries, leaving the voids wider and the filaments richer. The universe does not build only by adding light. It also builds by making absence larger. The local void lies near the local group, close in the enormous sense used for galaxies. It is a nearby underdense region, adjacent to the sheet of galaxies where the Milky Way and its neighbors are found. Its presence affects motion. Galaxies are not only pulled toward mass concentrations, they can also appear to move away from emptier regions because the surrounding denser structures pull more strongly from other directions. A void has influence not because it reaches out with substance, but because the missing mass changes the balance of gravity around it. Farther away, larger voids become part of the cosmic map. Some are tens or hundreds of millions of light-years across. Their borders are not sharp walls, but zones where galaxies become more common, where filaments cross, where clusters form like bright knots along a net. Inside the voids, galaxies can exist, but they tend to be isolated, faint, and less disturbed by the crowded interactions found in clusters. A galaxy in a void may live a quieter life, with fewer neighbors to pull at its shape. This makes voids useful. They are not only empty backgrounds, they are laboratories for cosmology. In dense regions, many processes overlap. Mergers, hot gas, feedback from black holes, starbursts, stripped atmospheres, and the tangled gravity of clusters. In voids, some of the noise is reduced. The motion of galaxies, the growth of structure, and the behavior of gravity can sometimes be read more cleanly because there is less luminous matter in the way. There are also larger claims that must be handled carefully. The KBC void has been proposed as a vast underdense region surrounding the local universe, and some studies have explored whether living in such a region might affect measurements of cosmic expansion. The idea is debated. It does not replace the standard picture by itself, and it is not a settled explanation for the Hubble tension, the mismatch between different measurements of how fast the universe is expanding. But it shows why voids matter. Even emptiness can become part of the argument. The cosmic microwave background adds another layer. This radiation is the cooled remnant glow from the early universe, arriving from every direction as a faint microwave signal. It is almost uniform, but not perfectly so. Tiny temperature variations in it correspond to early density differences, the seeds of later structure. One region, often called the cold spot, has drawn attention because it is unusually cool and large. compared with expectations. A possible connection to a supervoid along that line of sight has been proposed, though the full explanation remains unsettled. The honest answer is that not every anomaly has a finished story. The cold spot may involve a large, underdense region, or statistical chance, or a combination of effects not yet fully separated. Cosmology often works this way at the larger scales. The measurements are precise, the maps are beautiful, and still the interpretation may remain open. Past the voids, the journey does not end at darkness. It turns backward, in time. The James Webb Space Telescope looks in infrared, the kind of light stretched from the earliest galaxies by the expansion of the universe. When light travels for more than 13 billion years, space expands while it is on the way, and its wavelength lengthens. What began as visible or ultraviolet light can arrive as infrared. Webb was built to see that old, reddened light, to look toward the era when the first galaxies were forming and the fog of neutral hydrogen was beginning to clear. The early universe was not transparent in the way later space became. After the first atoms formed, much of the cosmos was filled with neutral hydrogen. The first stars and galaxies produced energetic light that gradually ionized this gas, a process called reionization. Webb is now finding galaxies from within that early period, some appearing surprisingly bright or mature for their age. These discoveries do not mean the old models simply vanish. They mean the details of early galaxy growth are being sharpened under better light. One galaxy, seen only a few 100 million years after the Big Bang, has shown unexpectedly strong hydrogen emission, as if a clear channel had already opened through the surrounding early fog. Another distant galaxy candidate has pushed observations still closer toward the beginning, showing how quickly structure may have gathered in the young cosmos. These are not nearby places. They are old light arriving now. Looking outward becomes a form of looking back. This is the final reversal of scale. The nearest spacecraft need hours for their signals to return. The nearest stars answer after years. Andromeda answers after millions of years. The earliest galaxies answer after more than 13 billion years. Distance becomes time because light has a speed, and the universe has a history. The observable universe is the part from which light has had time to reach us since the beginning. It is not necessarily the whole universe. It is only the visible horizon around one location in space-time. Beyond it may be more universe, perhaps much more, but its light has not arrived, and perhaps never will if expansion carries it away too quickly. The horizon is not a wall at the edge of existence, it is a limit of contact. So the journey that began with small spacecraft, leaving the sun, ends not at an object, but at a boundary of seeing. There are worlds without stars, black holes without surfaces, galaxies with fossil halos, voids that shape motion by what they lack, and early galaxies whose light crosses nearly all of cosmic time. The universe is not only the bright things inside it, it is also the distance between them, the darkness around them, and the ancient light still arriving through the dark.